Hi, welcome to this lesson on Euclidean geometry, ratios and proportions. Let's have a look at a revision of ratios and proportions. So we'll start off with the definition. A ratio between two quantities is a defined relationship that describes one quantity, let's call it A, with another quantity, let's call it B, of the same unit measurement. That's really important. So when we are describing two quantities in some sort of ratio, they need to be in the same unit measurement. All right, so we write the ratio of A is to B as this mathematical notation, A colon B, and read it as for every amount of A units that you have an amount of B units in comparison to that A units. So when we compare the two quantities, we are considering them as the same unit measurements. So for example, if you were comparing a building of 30 meters to a ruler of 30 centimeters, it wouldn't make sense to compare them in that unit measurement because one's in meters and one's in centimeters. You would either have to convert the centimeters to meters or the meters to centimeters so that we are comparing the same unit measurements. So why do we need to do this? Because if we consider the same unit measurement, we take that into account, then we are only comparing the actual magnitude or the numbers of the two quantities. So for example, if you have 3 kgs of a certain food A, and so for every 3 kgs of unit A that you have, could be rice or whatever, you need a 5 kgs of another food item, maybe flour or something, right? So that might be in a certain recipe. For every 3 cups of flour you put in, you need to add 5 cups of rice that goes with it, something like that, right? So you would compare the actual magnitude of the two numbers that have the same unit measurement. So you can drop the unit measurements and just compare the actual magnitude of those two. So let's have a look at an example. A rectangle having length of 10 centimeters, right, and a width of 4 centimeters can have the following comparisons in its two dimensions. So if you compare the length as opposed to the width, we can write that as for every 10 centimeters of length you need 4 centimeters of width. All right, and this can be simplified down by taking out a common factor between the two numbers. So because the units are the same, we compare the magnitudes, and 2 is common to both. So I can divide into 2 into each, and I get 5:2. So we say that this ratio is 5:2. So for every 5 units, in this case centimeters of length that you need 2 centimeters of width. So because we have 10 centimeters of total length, that means from 5 to 10 you multiply by 2, you do the same thing, right? It's what we say is in proportion. So this ratio now becomes 2 times 2, which is 4. So if we need 10 centimeters of length, then we need 4 centimeters of width. Another way of seeing this ratio is that a ratio is essentially a comparison, so it's a fraction. It's comparing a unit over another unit. So we can say the length divided by the width, 10 centimeters divided by 4 centimeters. Okay, so this kind of mathematics is called dimensional analysis because it deals with dimensions, in this case lengths and widths. So because the unit measurements are the same, we only compare the magnitude of the numbers. So in this case, 10 divided by 4 is 5/2. And you can see that this looks as it's in the same proportion. Length to width, 5:2. And that's exactly what we have here. All right, so in context, if this rectangle represents, for example, the fencing of a certain agricultural crop, then a farmer will need materials to build this fence. So if the optimal rectangle has a simplified ratio of 5:2, that means for every 2 units of material needed for the width, he will also need 5 units of that same material for the length. Okay, so notice that this is a simplified ratio, that 5:2, for the dimensions. And when we scale it up by a common factor, it still preserves the original ratio, right? So for example, when we had that rectangle of 10 centimeters to 4 centimeters, let's say the farmer actually needs a bigger fencing because there's more crop that's going to be growing, then he'll need, let's say, 20 centimeters of length of that fencing. But because the optimal way of creating the rectangle is in the ratio of 5:2 in his case, that means since he went from 10 to 20, he multiplied by 2. That means he needs to preserve the ratio, so he needs to multiply 4 by 2 to get 8 centimeters. All right, so this means if we scale the dimensions to be 20 centimeters by 8 centimeters, then we will still have a simplified ratio of, if you divide the length and the width, 20 divided by 8 still gives you 5/2. So it's still within that optimal simplified ratio. So let's have a look at this definition. If two or more ratios are equal, then we say that they are in the same proportion to each other. So this means that proportionality explains the equality of ratios. Mathematically, we can represent proportionality as follows. So we say that if A is to B is the same thing as C is to D, because A over B is the same thing as reading the ratio A is to B, and C divided by D is the same thing as reading the ratio C is to D. So we say that the A and B are in the same proportion as C and D. Okay, so what do we mean by that? So for example, let's take 10 divided by 2 and 20 divided by 4. Now 10 divided by 2, that is 5, and 20 divided by 4 is 5. So we say 10 and 2 are in the same proportion as 20 is to 4, right? 10 is 5 magnitudes more than 2, and 20 is 5 magnitudes more than 4. That's the way you can interpret it. Or you could say 2 is a 1/5 magnitude of 10, and 4 is a 1/5 magnitude of 20. They're in the same proportion to each other. So from this, we can deduce the following. So if we know that this proportion is true, A over B is the same as C over D, then we can do some algebraic manipulation and get some different interpretations. So for example, if I cross multiply both sides, I get A times D equals B times C. That is a true statement if this initial statement here is true, if those two quantities are in proportion. We can also flip the switch on them, as to say. So we take the reciprocal. So we can take B over A and flip over D over C, and we get this equality here is also true. We can also cross divide both sides. So I can divide both sides by C and bring it down here, and I can divide both sides by A. No, not A. So I'm going to divide both sides by C. So let's start off with the original. A over B equals C over D. So what I can do here is divide both sides by C and then multiply both sides by B. So if I do that, I'm going to get A divided by C, okay, and then that B is still in the denominator, but I'm going to multiply both sides by B, so it becomes B over D. Okay, and that's that equality there. And from that third equality, you can also flip the switch here and do the reciprocal. So we can get C over A equals D over B. So there's various algebraic manipulations we can do just from one proportion. And we would need to do these algebraic manipulations in order to solve a question depending on the context of the question. So we should always keep that at the back of our minds. So let's have a look at this example. Consider the following line segments. So line AC, and then there's a point B that cuts the line AC. So if we let the length of AB equal X and the length of BC equal Y, then if we take another line and essentially scale this length AB by some factor K, right? It could either increase the length or decrease the length. And we do the same thing for BC. We will multiply it by that same factor K and either shrink or increase. In this case, it looks like the line is increased. So because we multiply by the same factor, we assume that this should still be in the same proportion, and we can check. So if I do the length AB divided by the length BC, that is X divided by Y. And if I do the same thing here on this side, DE divided by EF, I get KX over KY. Now because K is the same, we can assume here K is not 0, otherwise the line would vanish. Then you can divide the K's out and you get X over Y. So we say that AB is to BC is in the same proportion as DE is to EF. Okay, similarly, you can also say DE over AB. So now you can compare from two different lines. So in the first case, we compared distances within the same line, right? Now we can compare distances from both lines simultaneously. So if I do this DE divided by this AB, right, and then I keep in that same pattern, then I'll do EF divided by BC. So if we do that, DE over AB, that's KX over X. Okay, and again, we can assume these lengths are all non-zero. Otherwise, we wouldn't have any lengths here at all. Then those will divide and you're left with K. And then EF over BC, that's also KY over Y, and you're left with K. So we say that DE to AB is in the same proportion as EF is to BC. The crucial concept regarding proportionality is the various algebraic expressions we can derive, okay, just from that one proportion as we've seen before. This can be visualized with regards to the line segments example. So if we look over here in this line segments example, AB over BC we saw was x over y, which is in the same proportion as DE is to EF, right? And you can flip the switch on that and do the reciprocal. So you can say BC over AB, which is y over x, is the same as EF over DE, right? You can also do cross multiplication. If I multiply AB times EF and then BC times DE, you will end up getting KXY for both, and that is in the same proportion as well. Okay, and you can do this for any of the other line segments in that example, as long as you follow it properly. So let's say, for example, this one here, BC over AC. So BC is y, over AC, the entire length, is x plus y units. Okay, so I need to keep in that same proportion. So since I took BC here, I should take EF here, which is KY, right? And then DF, which is the entire length here, is KX plus KY. So it'll be KY divided by KX plus KY. But I can take out KY as a common factor, or K as a common factor in the denominator. And you can see those all divide into each other, and you're left with Y over X plus Y. And that is exactly what BC over AC was. Okay, so as long as you take the ratios in the same sequence, essentially, then you will get the same proportions coming out. All right, so that is how we will deal with revision of ratios and proportions here. Essentially, the main goal is that once we've given a certain ratio, we know a ratio is true, and we compare it with another ratio, we can use the proportionality and algebraic manipulation to get a desired result that we are looking for. All right, I'll see you in the next one.